All right, our second lecture for the week is on organic nomenclature. And these are going to be molecules containing carbon. And we're using butane as an example to look at how the formulas are written for organic molecules. And the first one is going to be called the molecular formula. And this is just the ratio of the carbon and hydrogen atoms by number. And you don't get too much information from just the molecular formula. Next, I gave you this three-dimensional depiction. Lots of times when you see molecular models, you see this kind of thing. And the black is going to be the carbon background, the 4 carbons. And then the whites, you can count, there should be 10 there for the hydrogens. And you can see later on we'll study tetrahedral geometry, and that the hydrogens are arranged in a tetrahedral manner, which gives it that 3D structure. But anyway, look at the backbone of the molecule and see that it's kind of zigzag, which relates to the bond line formula below. But before we get to that, if we have 4 carbons, 1, 2, 3, 4, and then we can arrange them in a row and count out 10 hydrogens. Just place them around. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So that's 10 total. So actually, let me just take a minute here and make a drawing on the side. So you want to note something about carbon here. And if I were to draw out the structural formula, I would want to have carbon having 4 covalent bonds. So we have the first one drawn, and then 1, 2, 3, 4. The carbon next to it has 1, 2, 3, 4. Carbon next to that has 1, 2, 3, 4. The carbon next to that has 1, 2, 3, 4. And then you can just go around and put the hydrogens in, and that should work out to be 10. So you want to use that rule that the carbon has to have 4 bonds, and you wanted to, in the case of butane, they're all going to be single bonds. All right, now you can work with the structural formula here and see that this part, I'm going to do that in red, hold on. So this is referred to as the methyl group. And we denote that below in the condensed formula as CH3. That's the methyl group. Then you have the methylene group next in the formula. And if you were going to write the condensed formula, you would write that as CH2. Then you have another methylene group here and here. And then finally a methyl group at the end. The methyl group is CH3. So to go back and forth between the structural formula and the condensed formula is easy. Right, finally, the most unusual one is this bond line formula. And you want to remember that each point here is 1, 2, 3, 4 corresponds to 4 carbons. The hydrogens are there, and the hydrogens are assumed. You do not have to put them in. So organic chemists like to use the bond line formula, and this is going to be a representation for butane. All right, so you have these 5 different ways to indicate butane. There's actually more than that, but we'll stop here for the moment. All right, now we want to differentiate between saturated and unsaturated hydrocarbons. Saturated is all single bonds. Unsaturated hydrocarbons have either double bonds or triple bonds or both for at least some of their bonds. So the alkanes, you see the ANE, that tells you that the molecule is saturated. And you notice this formula here, CnH2n plus 2. We'll come back to that in just a minute. So if the molecule is saturated, then that means it's got all single bonds, and you want to use ANE to indicate that. So the first molecule here, CH4, you're going to use meth because that indicates 1 carbon, and then you're going to say ANE to tell you that it's saturated. So the structure for methane, again, 1, 2, 3, 4, right? It's saturated and it has 4 bonds. Now, if you look at the formula for methane, CH4, you could double the number of carbons, which is 2, and then add 2, and that would give you the number of hydrogens. So this fits the formula CnH2n plus 2. Now ethane is next. Ethane is named CH3CH3, or C2H6, is named ethane because it's got 2 carbons. Okay, so the prefixes are meth, eth, prop, 1, 2, 3, like that. So it's got 2 carbons, it's eth. It's saturated, meaning there's no double or triple bonds, and so we're going to call this ethane, A-N-E. Tells you that it's saturated. So ethane is C2H6. Notice if you double the number of carbons, 2 times 2 is 4, and then you add 2, you get 6, which is consistent with the general formula for alkanes. Alright, and then decane, you can see that one's got 10 carbons, and if it's a C10 saturated molecule, you're going to double the number of carbons, which is going to be 20, and then add 2, so it should be 22. Hopefully that's right. We've got 3, 5, 7, 9, 11, 13, 15, 17, 19, 22. So it's got 22 hydrogens. Alright, so that's how it goes. If it's just a straight chain, that means they're all in one long line. And you can imagine that zigzag configuration, which we're going to study later. Alright, now, it's never that simple. You can see with this molecule that you've got 1, 2, 3, 4, 5, 6, 7, 8 carbons. We're going to call that the main chain. So we're going to name the main chain octane because it's got 8 carbons and it's saturated. But there's actually another trick. You just can't be satisfied with that partial name yet. You really want to count and make sure that there's no other chain in the molecule that's longer. So you could say 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So it does appear that the chain as written from left to right is the longest chain, 8 carbons, so we're going to call it octane. Alright, now YL we'll use when we add groups to the main chain. So if it's got 1 carbon, this is going to be methyl, and if it's got 2 carbons, that'll be ethyl. So the big question here is the numbering, and I think I'll just take the trouble and write it out here. So you can either number the main chain as 1, 2, 3, 4, 5, 6, 7, 8, or you could number it as 1, 2, 3, 4, 5, 6, 7, 8. The molecule really doesn't know the difference between left and right. It's moving around in space. It's not a straight line. It's zigzag geometry, tetrahedral geometry. So there's no reason, to make anything special about the fact that the main chain here is going from left to right. So the numbering can go either way, and the goal is to make the numbers as small as possible. So there's going to be 2 ways you can number it. One would be to have the methyl groups, use the blue numbering. You could have the methyl in the 6th position and the ethyl in the 4th position. So when we write it out, we start with the lowest number first. So one possibility is 4 ethyl and 6 methyl. Okay, that's going from right to left using the blue numbering. The other possibility is going from left to right, where now the methyl would be in the 3 position and the ethyl group with the 2 carbons would be in the 4 position. So it would be 3 methyl and then 4 ethyl octane. Okay, so first you pick the main chain, then you work out the numbering associated with the substituent groups that are added to the main chain. Now, if you look at these two, you're going to pick the one that is that has the smaller numbering. Oh, that's yellow. It's not coming out so great. But the one below, this one, that's not very good. I'm just going to circle it in red. The one below happens to be the better choice because 3 and 4 are smaller in number than 4 and 6. So 3 and 4 is smaller than 4 and 6. Therefore, the second one is the correct choice. And that's what we named it on the top there. Okay, let's do one more of these for. And this one, we'll use the condensed formula so you're comfortable with that. Okay, and we have 1, 2. We have this one, and 1, 2, 3. Okay, so now we have to count, and we're just going to look for the smallest chain first, the longest chain first. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So it looks like the main chain is going to be this one right here. So the numbering either is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, or the numbering is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9. All right, so our choices then are, for the red, we have this methyl group. Okay, this right here is kind of hard to see, but that's a methyl group. So the end point represents 1 carbon, so that's methyl. On this one, we've got 1 point, 2 point, 3 points, so it's propyl. Okay, so then for the red numbering, it would be 3 methyl and 5 propyl, and then nonane. And then the other choice would be the blue numbering, which would give us 5 ethyl and then 7 methyl, nonane. Okay, so we're going to choose this one as the correct one because the 3 and the 5, the 3 and the 5 is smaller than the 5 and the 7. All right. So that's the story with the saturated hydrocarbons. When you start adding the substituent groups, notice that it's always YL. YL. Use YL when you're adding to it. And again. All right. So now, what happens if you have a double or triple bond in the molecule? And first of all, let's recognize what we have here. The first one has got 2 carbons. That's going to be F. And if it's a double bond, we're going to use ENE instead of ANE for the last molecules that we studied, for the saturated molecules. These are unsaturated molecules now. The common name is ethylene, but ethene is the systematic name. So let's go ahead and draw ethene, and it's got 1, 2 carbons. Each carbon has 1, 2, 3, 4, and then you count 1, 2 again, and then 3 and 4. So each carbon has 4, and then you can put the hydrogens in. Okay, so notice that there are 2 carbons and 4 hydrogens, so that's going to fit the formula CN and H2N if the molecule has 1 double bond. Alright, now butene is interesting because there's 2 ways we can draw it, and I think I need another page for butene. Let's see what I got here. Yep, okay. So for butene, you could have 1 butene or 2 butene. So if you had 1 butene, that means the double bond is at the end. So 1, 2, 3, 4. The double bond is at the end of the molecule. And basically the number 1 in the name comes from the very first carbon here. The double bond starts at the first carbon, therefore it's going to be number 1. Alright, now each carbon has 4. This carbon on the left already has 2. 1, 2, 3, 4. That's going to be for the hydrogens. Whoops, that's just a single bond there. Okay, the second carbon, you've got 1, 2. You're going to add 3 and 4. And then the third carbon is 1, 2, 3, 4. The fourth carbon is 1, 2, 3, 4. So let's put our hydrogens in. 1, 2, 3, 4, 5, 6, 7, 8. So C4H8, that is consistent with having the double bond. Alright, now you can have 2 butene, and lowercase is fine for this. And so you want to have 1, 2, 3, 4. This time the double bonds in the middle, and then you get single bonds. 1, 2, 3, 4. 1, 2, 3, 4. This carbon, third carbon, 1, 2, 3. One more makes 4. The last carbon is 1, 2, 3, 4, like that. Okay, so put the hydrogens in. Okay, so you can see the symmetry in that molecule. In between the 2 middle carbons, there's a point of symmetry. All right, now one thing we do with the 2 butene is we can think about these methyl groups and where they are relative to the double bond. So later on we're going to learn about Vesper structure, but let me draw a line here. This is 2 butene. One of them, 2 butene. One of them will have the 2 methyl groups on the same side of the double bond. That's referred to as cis-2 butene. And then the other structure is to have the methyl groups on opposite sides of the double bond. You can do this because this molecule is planar, and this is called trans 2-butene. Okay, so not a main topic, but one that is important enough in organic chemistry. You want to know the difference between cis and trans when the double bonds are present. Okay, so then, let's see, I had a page of notes here. Okay, all right, so I'm going to do one more page, and this molecule is 1, 2, 3, 4, 5, 6. So there's 1, 2, 3, 4, 5, 6, 7 carbons. You can put a methyl group here and make this one a double bond. That looks kind of bumpy, but that's supposed to be double bond there. Okay, so for this one, let's see. we've got 1, 2, 3, 4, 5, 6, 7 as the main chain. So it's going to be heptene, ENE, because of the double bond. So I brought this one up because you can choose now for the numbering. Actually, let's put some numbering in there. So 1, 2, 3, 4, 5, 6, 7. Or you could say 1, 2, 3, 4, 5, 6, 7. And the correct numbering here is that the double bond starts on carbon 2. And here we say that the double bond, whenever there's a double bond in the molecule, it will take priority over any other kind of substituent group. In this example, it's the methyl group. So it's going to take priority. The name of this molecule is going to be, what do we say, carbons? There's 7 carbons, so it's going to be heptene, and it's going to be 2-heptene. So 2-heptene, and then the methyl group is the red numbering there, so the methyl group is in the 5 position, so 5-methyl. Alright, so the double bond takes precedence over the methyl group, and therefore the numbering is associated with the position of the first carbon and the double bond. Okay, and this is going to be one with a triple bond, just so you can see what it looks like. So you don't have that bending with the triple bond, it's actually linear. Okay, so the bond formula is going to look more like this. 1, 2, 3, 4 carbons, 5, 6, 7, and like that. So let's see, 1, 2, 3, 4, 5, 6, 7 carbons, and similarly the numbering is going to be dictated by where the triple bond starts. So it's going to be 7 is hept, triple bond YNE, so it's going to be a 2-heptine, and then you've got 1, 2, 3, 4, 5, 6. This methyl group is in the 6th position, so it'd be 6-methyl. So the position of the triple bond takes precedence over the position of the methyl group in the molecule. All right. Now, next is, I'm going to back up one more. Here's an interesting molecule, benzene, and I stole these structures from the internet. And I wanted to give you one more to start with. So the formula is C6H6, and basically you've got a cyclic molecule that has alternating single and double bonds. Okay, so if there's only 6 hydrogens, you're going to put them in, and you're counting 4 again. So first put the hydrogens in, and then just pick this carbon. So you got 1, 2, 3. You're going to need one more. We'll put it right there for that one to have 4. So now this carbon has 1, 2, 3, 4. Now this carbon has 1, 2, 3, 4. Okay, this carbon needs another one, and see how they're going to alternate now. So now this carbon has 1, 2, 3, 4. Now this carbon has 1, 2, 3, 4. This has only got 3, so we're going to add one more double bond. We'll put it there. Okay, now look at this depiction. It's the same as what's on the left, except that we're not writing carbon here. Okay, it's just points of intersection of lines. There are the points for indicating carbon. Now here is an even simpler depiction of what we have on the left. Now we get rid of the hydrogens and the bonds. So this is a very typical symbol for benzene. The carbon and the hydrogens are assumed. Okay, this is the symbol that we use. Now, this next part shows something that you haven't seen before, so you got to stare at it a little bit. But the idea is that, you know, the double bond in one instant is here, okay, and then in the next instant it kind of hops over to this position here. So this double bond is the same as that, and then that electron pair moves over here, and then a new double bond is established. And the idea here is that in one instant you have alternating single and double bonds as shown here, and then in the next instant the electrons have moved, and now you still have alternating single and double bonds, but the double bonds are on the opposite positions. So that's how we think about benzene, that this kind of back and forth between the two structures. There's a theory called resonance theory, valence bond theory, which says that they're actual structures and they kind of oscillate back and forth. One molecule oscillates back and forth between the two positions. All right, and then you know, another idea is called molecular orbital theory. And now instead of having 3 distinct double bonds, we just let the electrons run together and then simplify this picture with the circle. So oftentimes you'll see a benzene ring and that benzene's just got a circle in it. And that means that it's got 3 alternating single and double bonds. All right, benzene's important, so it's good to go through that. All right, now cyclic groups are next, and notice that the cyclic groups are CnH2n, okay, and that would be like if you had a double bonded system, so it's just coincidental that they have the same general formula. You have to watch for that. But if you've got C3H6, you could draw the linear molecule with the double bond, but there's also this cyclic structure. So you've got 3 carbons in a ring, and it's CH2 at each point and the triangle. And then the representation is just this triangle. All right, then you have cyclobutane. It's got 4 carbons. We represent by a square. Cyclopentane. It's got 5 carbons. We represent by this pentagon. And then cyclohexane here. A and E tells you that there are no double bonds, so it's different. It looks the same as benzene, but it does not have the double bonds here. And then we represent that by the hexagon. Okay, so now we can talk about those molecules themselves, or we can look at adding them to the chain on a longer molecule. So let me look at my notes again. How about this one? All right, 1, 2, 3, 4, 5, 6. Put a cyclohexyl. When you're adding it to the main chain, you use YL. So this is going to be 3 cyclohexyl, and then the chain is 1, 2, 3, 4, 5, 6. So it's going to be hexane. That's it. You don't want to use 1, 2, 3, 4 cyclohexyl hexane. You want to keep the number 3, or the position of the cyclohexyl group, as small as possible. All right, now if you, let's see, hang on, yep. If you wanted to add the benzene ring, 1, 2, 3, 4, 5, 6, instead, the circle, you would think that you would use the word benzyl, but we don't. We use phenyl instead, P-H-E-N-Y-L. So this is 1, 2, 3, 4, 5, 6, 7. So that's going to be a heptane, and it'll be a 3-phenyl heptane molecule. All right, and then I have one more here. Cyclic group to the main chain that also contains a double or triple bond. And for this one, we can use maybe this 1, 2, 3, 4, 5, 6. Make it a double bond, and maybe put a cyclopropyl group. So there's, you got to see this. This is 1, 2, 3 carbons that are just bonded to this carbon, which is on the main chain. All right, now the double bond is going to take precedence over the position of the cyclopropyl group. And so the double bond starts in the 2 position, going from right to left. So this is going to be, hold on, 1, 2, 3, 4, sorry, that's wrong. Be 4 cyclopropyl, 2, and then 1, 2, 3, 4, 5, 6, 2 hexene. The ENE tells you it's got a double bond, and it's in the 2 position. I'm going to erase that stuff right there, make it look the way it's supposed to look. All right. Nope. Here, what is that? Okay, and then finally, these functional groups, you see many organic molecules that have atoms other than just carbon and hydrogen, and here are some examples with oxygen and nitrogen, and of course there are others as well. For these, you don't have to name the molecules, but you need to know the type of molecule it is. So for example, if you saw this structure, okay, that is going to be a ketone. And how do we know it's a ketone? The ketone has this CO group, and then it's got these 2 other groups. We call them R groups. So that's an R and that's an R. And then, so the structure is C double bond O and R and R. That's a ketone. So an aldehyde might be something like this, CH3, C double bond O, can't fit it there, and then a hydrogen. So how do you know you have an aldehyde? Okay, you got this, and then you have the R group, which happens to be methyl. The R group could be ethyl, propyl, butyl, benzyl, phenyl, cyclopropyl. It doesn't matter, just something with carbon in it. Okay, now the carboxylic acid one is a pretty important molecule. We talk about acetic acid all the time in chemistry, but there's a whole series of them depending on the length of the carbon chain. So the carboxylic acid group, you know by this COOH structure, and then it's got this R group on it. All right, then you can keep going. You got an ester, which has 2 R groups, an amide that's got 3 R groups, and a nitrogen. Ether is just oxygen connected to 2 R groups, and then the alcohols at the bottom, those are pretty important. So you could have CH3, CH2, CH2OH. That is going to be propyl alcohol or propanol. And why is it propyl? Because there's 3 carbons, and then it's being added to the OH, which is the alcohol. So propyl alcohol, or the other name would be propanol. That would be the common name. So can you recognize an ester? Can you recognize an ether? That's what I'm looking for. I don't want you to name them. I just want you to know the different groups that show up in a molecule. All right, and then I think that's that. So let's see. We could have maybe finish by doing something like this. Just for fun. Okay, there's a molecule that has an aldehyde group. You know that because the hydrogen C double bond O, and then it's connected to a hydrogen. This one is going to be a ketone because it's got 2 R groups. This one is an aldehyde. And this, of course, is a double bond. All All right, I think that's enough for today. I'm going to see you in a week. Thanks.